Okay, should we get started then?
Yes, I think so, Charity.
Okay, great. Well, welcome to Big Mountain Data and Dev session. This is Thursday's 2:15 session, room 3. And this is Mission Impossible DevSecOps. And I'll hand it over to Stephen.
Thank you for the introduction, Charity, and thank you for everyone who's attending. Welcome to Mission Impossible DevSecOps. Today, we'll be discussing the problems tech teams have building, delivering, and operating applications securely and sustainably. Let me introduce myself quickly. My name is Stephen Kuenzli. I'm founder of K9 Security. We help teams improve security policies and accelerate delivery processes. We do that by integrating security into delivery processes. And today I'll share the principles we use and recommend teams adopt to integrate security, spanning design through operations. It's a broad topic, and this is meant to be an introduction that provides ideas and examples you can take back to your team and consider for adoption. When you have questions, please submit them into the chat and I'll address them at the end or perhaps during the talk. All right. So let's start with a familiar scenario. Imagine you're an engineer on the fraud analysis team and your product manager comes to you 6 weeks before US retail peak, which is this week, unfortunately or fortunately, and says, hey, we really want to integrate data from this new partner. And we want to use it to model, detect, prevent a new variation of like householding fraud that's affecting our customers. Can you do it? And you discuss it for about 5 minutes and end up saying, yes, but we only have enough time to do the quickest thing possible. And product manager says, great, I'll let everyone and the partner know we're moving forward and it'll be ready for peak. And all of a sudden you're on the hook. And everyone works hard and puts some extra hours in because they know it's important. And yay, the feature ships and it lands in prod the Monday before Black Friday. And it's great. Publicly, the team is happy and everyone is celebrating. You know, you hit the date and it works and that's good. Like you should celebrate that. But privately, the team knows they cut some corners, particularly around security, and they're frustrated that they had to do that again, and they're fearful of a data breach. And the story isn't over. The system is in production, serving traffic, subject to attack. Where does the security story go next? Does the product management and delivery team do nothing and make no changes and maybe end up in the news? Or maybe they integrate security in their delivery process and adopt a safer path as a matter of course. And this isn't a problem of intentions. Engineers want to build great, safe products. Business wants to change faster, and customers need data security. The problem here is we're kind of in an over-constrained environment. Building and designing features, we're doing that. We're designing new features and delivering more changes instead of quarterly or annually. We're doing that monthly, weekly, or sometimes even daily for changes. And because security is actually hard and building safe systems is difficult, it won't just happen as a byproduct of intention. We have to have work done by people with special expertise. And just like data science, web dev, and 24/7 operations, like this is a real specialty. So in over 20 in-person interviews with people like you, engineers, scientists, team leaders, the answer to the question of like, why is security hard? There's a couple themes or 3 themes. 1, it's hard to get security right. 2, it's difficult to validate, even for experts. And 3, small changes can cause big problems, particularly for unseen things like forgetting or like not realizing you needed to close off access to something. Like maybe you enabled access for certain things, but you needed to close off access for something else, for other people. And that hole is very common. And the people who are doing this often get overloaded and projects get delayed, or we defer security until tomorrow, because you don't have endless time to dig through blog posts and API docs to implement security controls. And on top of that, continuous delivery and infrastructure automation is pushing the rate of change even faster. Robust scientific research by Dr. Forsgren and others presented in the book Accelerate shows that delivering changes quickly with low lead times is a characteristic of high performance teams and driver business outcomes. So not only is the rate of change not going away, it's going to accelerate. And there's science for that now. So now I'd like to introduce some concepts to help us combat this, or that will help us combat this, from the field of safety and reliability engineering. In particular, Dr. Levison, who is a leader in safety engineering, says that safety is a system property. And we cannot guarantee the safety of data managed by a system by only examining or making individual components safe. The interactions matter a lot. Additionally, information security is an aspect of system safety. And there are many hazards to information security that can result in real harm to physical, business, and financial losses. If you're interested in systems engineering safety, I highly recommend you check out her book, Dr. Levison's book, Engineering Safer World. It's fantastic. And I should love to chat with you after about that. And fortunately, systems thinking provides a path forward. So we can treat safety as a dynamic control problem. Again, this is Levison, who developed a whole model around this idea called STAMP, which we don't have time to drill into here, but is lovely. And instead of looking for individual classes of failure events in running systems, and then trying to prevent them one by one by plugging holes in cheese or a magic firewall, we define and establish safety constraints for the system and let the control system enforce and converge operations to desired state quickly. So the familiar analogy, or a familiar analogy, is a thermostat that manages a building's climate. We ask the thermostat to maintain a comfortable temperature constraint, perhaps by saying keep the temperature in the range of 68 to 76 degrees Fahrenheit. And the thermostat will activate the heating and cooling systems to do just that. Similarly, in the information security realm, we could define a least privileged access for confidential data constraint that says a minimum of 1 and a maximum of 5 authorized principals may have access to confidential application data. And that provides enough room for the application backup processes and maybe, say, a tier 3 customer service team to have access to that data. And if we gather enough information, and now that we've modeled that, we can gather information and run that through a controller that helps us ensure that that's true across our systems. The point here is that we let machines detect the problem and put people in control with high leverage solutions. Most systems are going to have many safety constraints, like 10 or more that guide its design, development, and operations. And it's important to think about these things up front, or certainly more efficient. And if we adopt the posture that the world and system are always going to be changing, and thinking new vulnerabilities are going to come up, we need to reposition ourselves around the notion of we need to be able to change the system and update the system quickly and confidently to keep the system out of hazard states. So hopefully, or that shift in emphasis might be straightforward for you. And so that's great. Assuming you've made or willing to entertain that shift, we can move forward with how accidents happen in this model. So accidents happen when system constraints are missing or not successfully enforced. So we start by defining constraints, and in information technology, we're often going to have constraints that we define at the organization or business unit level. So perhaps we have a data warehouse and a B2B department, and they may also vary by stage of delivery. For instance, we might have a rule that says deleting a database is okay in dev, but never in prod. And events leading to losses occur because safety constraints were not successfully enforced or are missing. And in my experience, the missing constraints are a big problem. Many, again, going back to those interviews, many engineers and technology teams report not having sufficient security frameworks and architecture to work with. So going forward, we need to define safety constraints to succeed in this model, and then we need to engineer them into the system. There's no silver bullet, as I said. Firewalls and data loss prevention tools are useful components, but they're not a full solution because safety is a system property. So if we return to our fraud analysis team, the fraud prediction system might have a subset of safety constraints that look like this. These constraints are organized into the classic confidentiality, integrity, and availability, threat and risk analysis categories of information security. And we have some org level constraints, such as only deploy artifacts in appropriately secured configurations, and only an app level constraints like predict using only valid data. Critically, the application and supporting teams, collaborating teams, now know, once they've defined these constraints, what they should be doing to stay safe and can work on implementing those controls. And this integrates directly with information security, which is the practice of identifying and prioritizing threats to information confidentiality, integrity, availability, and coming back out of the constraints definition, implementing controls that help the organization manage risk. So security controls try to prevent threats to information from occurring or help you respond to a threat. And there are two major classes of controls, preventative and detective. And authentication and authorization schemes like usernames and passwords allow the system to limit that user to only their own information, and that's a preventive control. It's also smart to log which user actually accessed given data, so you can verify that users aren't accessing data they shouldn't have access to, and create an audit trail to examine if something might be wrong. If you then implement an alert that fires when a user accesses another's data, you've created a detective control. Much effort has been spent on detective controls, and many organizations have a solid detective game. More effort is being spent on preventive controls, and most organizations will find the best ROI and want to focus here for future work. Generally, most preventive controls are involve integrating earlier in the delivery lifecycle, and that's what DevSecOps is all about. We'd rather prevent problems than detect and fix them. So complicating this is that cloud and traditional data centers are quite different. They differ in both best and common practice, which creates communication problems for security, cloud, DevOps, app teams, like basically everyone involved. Some of the major changes occur in cross-technology organization and delivery process. So in the technology domain, there are many more choices. There are many more services. For example, each hyperscale cloud has over 100 services. And there's an explosion of identities, policies, and capabilities. So, your applications are running at fine-grained identities. Maybe a container gets its own, like the fraud application we're going to see in a minute, like the ingest activity might have its own identity. And this represents a big shift because network identity and firewall is being replaced by these compute platform identities and cloud security policies, and it's a big shift. So in cloud platforms, the compute service is tightly integrated with networking and identity and access management services. And this allows the compute service to provide each compute instance with a strong trusted identity that's portable across the network and can be used to access infrastructure services such as storage and queues. And that's very different from a lot of people's old model of permitting traffic between certain IPs or subnets. Organizational models are significantly different, and I'll simplify this to more autonomy. The main thing is that cloud teams expect to have more autonomy to build, design, and deliver using self-service provisioning of cloud resources. Not running through that central teams anymore. And teams take advantage of that autonomy to deliver at higher rates of change and lower latency per accelerates results. And because security controls are intertwined with technology, org, and delivery process, all these security controls need to be updated. The old ones are unlikely to work. We'll skip details of why that is for now, but we can return to it in Q&A if there's time. So we must update our approach to security. And we need to integrate security into our software delivery process to enforce our safety constraints. And this is the best way we know of, at least, for us to support the increased rates of change, increased choice, and scale of our systems and organizations. So I want to move into the integration phase now the delivery phase, or delivery process. And so each phase of the software delivery lifecycle enables us to build confidence about the safety of the system, but it does so in different ways. In the design phase, we expect to plan our safety constraints and key security controls. Good design sets up the project for success and eliminates a lot of rework and late surprises. I'm not saying don't be agile, I'm saying flush out big questions early and figure out what you don't know as soon as you can. We expect the build phase to produce software and infrastructure code is mostly free from vulnerabilities and aligns to our security standards. The artifacts should be ready for deploy and published to a trustworthy repository once they exit the build phase. The deploy phase should deploy our actual system to the state defined by our infrastructure and other system configuration management code. We can use system and functional tests to verify the system is operating safely, even when overloaded or attacked. And as we run those tests, we promote it through different environments. And in the operational phases, for both non-production and production environments, we expect to verify that the application and infrastructure produce telemetry that makes the system observable, so we can monitor it, and provides controls operators can use to manage the system. And we should verify that those controls actually work pre-production. Historically, most security controls have been focused first in the operate phase, detecting problems using log analysis or implementing access controls using network access controls. And secondarily, in the build phase, detecting vulnerabilities in the software supply chain. So we're going to build on that good work. And while we're doing this, we're going to collect feedback from each phase and send it back into the design and build phases. So returning to our intrepid fraud analysis team, how could we deliver securely and hit the date? Suppose that this organization has architecture and integration standards. These standards can provide very high leverage both immediately in the design process as well as downstream in the SDLC. Standard architectures and integration patterns provide cohesive, logical building blocks that delivery teams can start with and have security issues largely sorted or thought through. And so the remaining design steps become much easier, elaborating a threat model and designing security controls and performing a review. This is good for both technical fit and also familiarity by engineers. So our fraud team, what they might do is after initial discussion with their partner, they looked in the architectural pattern catalog and proposed that they integrate with the partner using an SQSQ. And Amazon SQS stands for Simple Queue Service, and it's a standard event processing or event integration method in this org. And so that seemed like a good idea, but they weren't sure because they haven't used it for confidential data yet. The fraud team hasn't used it for confidential data yet. And they met with the security folks and they said, yeah, SQS is fine as long as the data is encrypted in transport and at rest using an encryption key controlled by the fraud application and fraud team. The queue security policy only permits the partner to write to the queue, and the queue retains unread messages for like 7 days. And further, the security team was like, hey, you should check out the infrastructure modules that the platform team has built because we've been through this sort of thing before, and they have some pre-made solutions. And we'll look at those opinionated infrastructure libraries in a bit. Security team also asked the fraud team to implement a data validation procedure that verifies the data integrity of the data coming from the partner because they've had issues in the past. And so, that's a narrative form of essentially what the threat modeling discussion looks like. And the initial reviews with the security team. And the fraud team said, okay, you know what, that's great. And they both worked together and came up with a way to detect bad data in real time and toggle the feature. And then the security and fraud team documented those information security threats in a threat model. And threat modeling is just the practice of identifying and prioritizing potential threats. And also security mitigations that protect information of value. And so, we've been talking about that a lot. And so threat modeling is a term of art in the information security space, but it's not that mystical. The fraud team captured the safety constraints and prospective security controls in these discussions in their design doc. And then they scheduled some work to investigate the details of the organization's infrastructure code components and how they're going to complete the design and review it. And before we're going to move on to the actual architecture in just a second, but the ROI on engaging security at the beginning of a change can be incredible. It's much easier, quicker, safer in the long run to incorporate the right security controls and take advantage of existing implementations early on than implement from scratch or tack on something at the end. So let's see. Right, because we need a plan where we're going to introduce our safety constraints and security controls. So here's the architecture that the fraud team picked and proposed. And it's a well-used pattern within the org. It's called integrate data security via encrypted queue. And access to the queue, the encryption key, and object storage resources can all be controlled with security policy. So it's straightforward to implement constraints like that were listed on a few slides back, such as only the partner may publish to its event inbox, only the fraud app data integration may update its model, and further, as data is ingested, the event processor notifies the model update process that new data is available, and that it also notifies the fraud prediction system's metric collection system that whether the data that's coming in is good or bad, and that can be subscribed or forwarded on to a feature controller that then can toggle data on and off and implement that predict using only valid data feature. Oops. So the supported architecture patterns in this org can be implemented using components from the organization's infrastructure service catalog. And this is literally a marketing page or directory that lists the set of supported infrastructure component offerings. These components have an infrastructure library implementation that implements common security controls and standards. And for example, the object storage component says it's built on top of the AWS Simple Storage service and is intended for storing files and does not support use cases that require direct indexing or queryable access. Because even though that some of that is actually possible in AWS, this org has chosen not to do that. The component page also describes features such as encryption in flight and at risk, fine-grained access controls, and describes the supported use cases or suggested use cases, and the location of the source code in the organization's Git repositories, or sorry, Git service. And that's a lot of the work in the design phase, is like basically coming up with the architecture, building a secure architecture, and identifying the secure components that you're likely to use, and how your controls are going to be implemented. And in the build phase, we're trying to ensure that software and infra code is mostly free from vulnerabilities and aligns to security standards and is ready for deployment to an integrated test environment. So we need to recognize that application vulnerabilities are exploited in about 70% of attacks, last I was reading. And to address that problem, organizations are and have been trying to secure their software and now infrastructure code supply chains. So we want to have trusted components for software building and for infrastructure building, because these supply chains are getting longer, they're getting more complicated, and they change quicker as our ecosystems grow. So it's important to choose a set of software dependencies you can keep up to date, and then integrate updates into your delivered software quickly. Whether quickly means monthly, weekly, or daily to you is mostly up to you and your security team or risk management team and its definition of safety. Fortunately, continuous integration and delivery make this much easier. Building, testing, and deploying new software artifact is no longer a big deal. Infrastructure libraries are both a new and an old thing. You can create libraries that model object storage, relational databases, container deployments, etc. And you can do that in tools like Chef and Puppet, or infrastructure management tools or like Terraform, Helm, Azure Resource Manager, etc. Many organizations have been collecting these in service or infrastructure component catalogs for years. I will point out one catch. What you will often find shared as open source or sold commercially as a infrastructure component is optimized for flexibility and convenience. And that makes sense because they want to maximize the number of users who adopt it. So platform engineers should work with their security and architect and other teams to compose those generic libraries within your own wrapper that configures those unopinionated components in ways that maximize your security and usability for your organization. You don't want every product team to have to think about how to secure an S3 bucket. They generally don't know how, and they don't have time to learn when they're trying to deliver by Black Friday. So here's what an opinionated module looks like. This is an example of what something you might give to a team that needs to configure a bucket policy that restricts access or configures access to an S3 bucket. And I want to emphasize that the interface to an opinionated module of this nature that's intended for consumption by delivery teams, its primary focus should be on usability. And so generally, you want to choose or enable the users to describe what they need in terms they understand. So you want them to describe like the confidentiality of data, perhaps, which principals should have access, and provide a consistent interface and semantics across your organization. And that's so that when you learn how to use one module, you feel right at home using the next, and there aren't semantic conflicts that the app team has to resolve when composing an application out of multiple modules. That's the last set of folks that you really want to have to figure out, like, well, actually these, confidential means two different things, or means different things in these two different modules. So on the inside of an opinionated module, you might have something that looks like this. And this is an example of a definition of a S3 bucket policy that's denying everyone else who is not explicitly granted access, they're being denied access. So this is an example of an often forgotten rule, which is deny access to people who don't need it. And it prevents your firewall, or it prevents issues like your firewall being able to read your credit applications. And very few people are going to get this right on even their own critical data, let alone in the general case across an org. And so you've got to codify the implementation to make it accessible and scalable across the org. And that means, going back to the interface, like, the people who needed or were permitted access, they were described in terms like allow administrator, allow read, allow write, and it wasn't visible there because it wasn't needed, but allowing delete. And those are terms that people understand. And this bit of code does the heavy lifting of figuring out, like, okay, well, these are we're going to deny everyone else through an exclusion. And this is actually how you can implement least privilege in a pretty reasonable way, or a more least privilege way than you're currently doing. And second, I highly recommend that you create modules that are secure by design and default. Like, I encourage you to hard code safety constraints, such as we require encryption in transit. Just do it. Like don't even make it an option to turn it off. Or if you do need to make it an option for some reason, which is often not a good reason, like TLS is, well established. And it's usually like really old and vulnerable software, or that is really old software that is vulnerable to other things that might need it. And so you need to actually consider carefully whether not you should turn off safety constraints. But at minimum, you should implement safe defaults and encourage in order to encourage their adoption. One thing I'll note here is that so these are some statements that implement or enforce encryption in transit and at rest. And it actually takes 3 statements in a bucket policy, essentially. And but one nice thing, this last statement that requires encryption with a KMS key provides a second layer or a second and potentially standard point of access control using KMS. And that's important. There's important features to have at an architectural level that you can depend on these sort of safety properties or security controls being like widely available and adopted in your org. Now, when it comes to like actually building an application with those opinionated blocks, what you ought to be able to do then as an application developer is compose apps from the organization's secure building blocks. And maybe you've got, an SQS, S3, and like a Lambda library that you all reference and pull from your internal private version control system. And what this enables is minimal decisions and configuration by the product team. And it also signals that if you're missing a component, you probably need to add something on the order of 2 weeks to the schedule or find another way, because building these things does take time. It's not 2 days, and it's certainly not 2 hours to build something that is cohesive and secure and can be used in a bunch of places. And so let's say, moving forward to like our scanning our code, which is, something that we're going to do before we publish it to our artifact repository to help ensure that it's in a deployable state. If we're using Python for our Lambda and deploying using Terraform, then we might choose the PyLint, which is going to find some things that are security related, and we might adopt a commercial tool such as Sneak or White Source to analyze our Python code for vulnerabilities before we let it move on. We might also use something like the open source DevSecOps tool to analyze our infrastructure code. It's important to recognize that these scanning tools are going to be different depending on what tech stack you use. Analyzing a Python serverless app is significantly different from a .NET web app on a Windows VM. And so you'll need to work with the security team to identify an appropriate tooling options and configurations to achieve what you need. But then the next step or the next phase in our delivery process in our journey of implementing security controls is deployment. And the primary tools for integrating security into the deployment process are systems configuration management, system configuration testing, and functional testing tools. And at a high level, system configuration management tools and processes ensure that what you have deployed is what you intended and put in and described in code. There are many tools for managing system configuration. Chef, Ansible, Puppet are great for managing long-lived application compute instances. Terraform, CloudFormation, Azure Resource Manager, Kubernetes deployment specs, etc., are great for what we now view as infrastructure. And the common thread across all these tools is they take your system configuration code as an input and then try to converge reality to that desired state. And they'll do that repeatedly and without tiring generally. There may be an exponential backoff in there, but they will keep at it. In the cloud, teams can also constrain what services may be used in specific operations like delete database with security policies that cover an entire cloud account. And so, you can think of those as system configuration management tools as well. On the system configuration testing side, some smart folks said, hey, let's check what is deployed complies with our enterprise or security team defined policies. And those tools have names like InSpec, ServerSpec, etc. There are also a number of config checking options becoming available within cloud systems that verify configuration of or detect interesting things about resources. Lastly, on this phase, we have functional tests of the public interface of the application, and they're critical. And both the web and native front end, as well as the public APIs, should have positive and negative checks for things like authentication, authorization that run not only on every deploy, but also periodically. So you can, I think about those as crossing over into like an operational monitoring sort of thing as well. And that's to like literally help you identify problems wherein maybe like you accidentally broke your password checking, like your password, your authentication mechanism, or the authentication mechanism failed to an open state because some dependency was down. So returning to the fraud team, their platform team supports using Terraform and deploying with Terraform Cloud when using AWS. So, they might, in this scenario, kick off functional tests that verify the app's authentication and authorization, as well as the feature flags and operation of that control plane that detects bad data and excludes the partner portion of the model from predictions. Let's see. So I guess, yeah, from a system configuration management perspective, the delivery team is going to declare their intended state using Terraform. That includes security policies, identities. Sometimes those security policies and identities are managed by someone else, but they're at least consuming them in those security and identity resources in their app deployment. And then they automate the deployment process with the platform supported tools. So Terraform Cloud, let's say. Now, at this phase, we also start to see interactions with the security and platform team from a system configuration management perspective. They might limit use of AWS to approved services and deny dangerous operations with service control policy. They might also be, and in this case, they're rolling out enforcement of their tagging standard with a tagging policy. But that's a work in progress because that service or feature just launched in AWS, I don't know, 3 months ago or 6 months ago. So they can't do it all at once. From a verification perspective, the security and platform team are verifying core AWS configs with AWS config and AWS security Hub's CIS compliant rule set, which is the Center for Internet Security's like best practices for or at least minimal practices for securing clouds. And they also use Cloud Custodian to identify unused resources or resources that were deployed manually or things that they just they're not even described. They detect configuration drift, which is critical for triggering a resolution or a reconvergence to state. And they trigger that configuration drift by running Terraform plan daily on every deployment and feed notifications to the log analysis and security incident event management system, which is often something like Splunk or Elasticsearch. And now finally, we've reached the operations phase. And network-based controls for preventing and detecting improper access have been a cornerstone of InfoSec and are still valuable. So network firewalls and segmentation often identify, partition, and authorize access. Web application firewalls and API gateways inspect live application traffic in order to detect and potentially block or at least audit potential exploits. Second, vulnerability scanning tools discover devices on the network and look for problems such as publicly accessible database and SSH servers. And vulnerability scanning tools also are deployed on individual network hosts and compute instances to discover and report operating system and software vulnerabilities that are actually out in the runtime of the application and are thus available for exploit by attackers, or most available. And even just having that inventory is very useful when some new exploit emerges. Third, there's the venerable log analysis, which aggregates, analyzes, and alerts on events that are interesting from a security and operational perspective. Good examples are unsuccessful login attempts or successful login with a privileged user, such as root or administrator. Fourth, but certainly not least, is identity and access management. IAM is the principal way to control access to data and services in cloud systems. In some traditional data centers, if you've made a significant investment in identity management. And with IAM, you can and need to manage access policies and the actual access, which is going to show up in an audit log. You need to watch those very carefully. You can also adopt tools that help you analyze and verify the actual access that IAM principals have to verify application and safety constraints are as you expect before a breach occurs. And that's because performing the thought experiment of who has access to what is actually really difficult and error prone. So in the case of our fraud analysis team and this fraud prediction system, it's serverless, so engineers focus on access to data. There's no material network or compute to protect because AWS SQS owns the input point. You know, they run SQS. And of course, like on the actual prediction serving side, there could be something, but we didn't talk about that today. But what this means is that even though there's no network and your compute is pretty trusted, it's running in serverless, it just receives an event. Now a lot of those network access policy analysis or network access questions have actually shifted to reviewing access controls implemented in IAM, SQS, S3, KMS, security policies. And so that actually goes back to something I just said, which is it's difficult to analyze that access manually. So they audit with commercial tools or things integrated into the cloud, such as AWS Access Analyzer or K9. But the security operations team, they are in the operational domain analyzing notifications and alerts in the SIM and escalating to application, platform, and security team as necessary. As problems are identified in operations as well as deployment, build, or even design, they're recorded in the app and platform team backlogs and prioritized weekly. So this is an example of like, well, when there are issues, we actually need to detect and respond to them, like improve the system, or at least accord them the respect they're due by prioritizing them along with other product goals. So some of the fraud team's security successes, they designed safety constraints with experts so they can be confident that this is actually a pretty good setup. They accelerated their delivery by building with trusted software and infrastructure components. They scan and remove some vulnerabilities early, avoiding rework. And so that's what created their acceleration. And being more secure didn't cost them any time because a lot of the engineering and work had been done previously, and they can basically compose and build on top of things. And ultimately, they ended up integrating strong access controls, and they achieved this feature of basically monitoring the integrity of their own data and automatically detecting and containing issues that might affect prediction. So, summarizing, you can secure deployments at high rates of change with an integrated approach. It's not impossible, and I hope this talk will help you on that journey. Designing and building secure systems is difficult. Define safety constraints and integrate security into your delivery process so you can deliver security continuously, quickly, and without a bunch of frustration or fear. Architect and build and share secure components and tools across your organization to save a ton of time and avoid schedule risk. Gather feedback and improve the safety of your systems continuously. And I just want to thank you for joining me in this session. I'd love to continue this discussion in the Q&A or on Twitter. My handle is @Kuenzli on Twitter as well as most places. And please fill out the survey. Myself and our organizers would greatly appreciate it. Thank you.
Great, thanks so much, Stephen. And that was our session today. We'll go ahead and end it now.